Let's now look at some of the more commonly used string library functions. So first I need the string library, string.h, and we'll create some character arrays to work with. Char A, char B, char C, right. So we're introducing the string length function that gives you the number of characters in the string excluding the terminating null. Let's go look it up. So string length is right here. Right? So it says it returns size underscore t. So this is really an alias to an unsigned integer type because the length is never going to be a negative number. So it's trying to give us the biggest possible number that it could, or give us the ability to represent a really big number is what it's trying to do. What does it expect to receive? It says const char star str. The str is the variable name within the function, or at least what we can see. It needs to be of type char star, so it expects to receive the address of a character. What it doesn't tell you is technically it expects it to be the address to a character that begins a null terminated array of characters, not just any character. And then the const is there, and that keyword says don't let this pointer change what it's pointing at. So really what we need to know is give it the address of a null terminated array of characters, and it's going to give us back an integer, a non-negative integer. So what about size of B? Let's see what this gives us. So B has 4 characters that I can see, ELSE, but it actually uses 5 bytes of memory. That's what size of tells me, because there's a terminate null. When you're counting characters, make sure you include spaces, because that's still a character. It has ASCII value of 32. What if we apply this to C though? So it says string length of C is 1. Size of is 50. The 50 is right. I've allocated 50 bytes. So what's happening here? Well, remember, I just said that the function expects to receive the address of a null terminated array of characters. Here I've allocated memory to store an array of characters, but it's uninitialized. So it's really just garbage values. So I could have gotten 1, I could have gotten something else, who knows what. If instead I had done this, and there's times you would do this, and there's times you would do what I'm about to show you. But if I do that, what is that? That's an empty string. So it consists of just a terminating null, which has ASCII value of 0. But since I told it to allocate 50 bytes of memory, or enough memory to store 50 chars, then the other 49 positions in the array will automatically default to having zeros as well. Now I get 0 from string length because there's no characters before the terminate null, so now it's correct. But before it was just an undefined operation. I couldn't tell you for sure what was going to happen. So that's string length. Let's look at string copy. Let's go over here and see how it works. there's string copy. It returns the address to a char. I think it's actually the destination, but I never use it. But what does it expect to receive? The address of a char followed by another address of a char. Once again, even though it doesn't specify it here, these should be null terminated array of characters. So what it's telling me is that this right here is my destination array. This is my source array, and it's going to copy the source array to the destination array. So if I put C here and A, now print C, it copied something over to here. A lot of the mistakes that people make when working with strings is not thinking about space and having enough of it. Here I put in 50, and so certainly something plus its terminating null, don't forget that, will fit into that. But you shouldn't try to force something that's too big and too small of an area. There it's hard to know in advance what's going to happen. What if I did this now? So now it's else. So what actually happened there? So it copied else over to the beginning, but did it do anything else? Let's look at it and see. So let's look at that array, or at least parts of it. We'll look at the first 10 locations. And what I want to do is print those characters. So to be C sub I. And I'm going to do this. X percent C. X. And actually it would be probably better this. Let's use capital A and capital Z. There's a reason for this. What I'm doing is I'm wrapping the character with two other characters, so that way if there's something that doesn't print, I still know where it was at. A lot of debugging is helped by knowing where something should be. And I use A and Z because there are times where maybe you slip a new line in there and you don't realize it, and the Z shows up on a different line, which makes it clear that there was a new line. That saved me a lot of debugging time doing that. So what I forget? Double quote. ELSE. Now A and Z are touching. What's happening there? And then HINGZ. Well, here's what happened. I created C like this, which means I allocated a block of memory that could store 50 chars. So since a char is 1 byte, it was 50 bytes of memory. But initially it was uninitialized. So then I wrote something there. Terminate null. And then some garbage. So that's not 10, that's backslash 0, sorry. All right. So now when I said to write else here, what it did was it put an E here, an L, an S, another E, and a terminate null in that spot. What about the rest of it? It just leaves it alone. I didn't say do anything with it, and I can't really with that function. It just starts writing the new string at the beginning, and it stops when it needs to stop. So the other characters are still there. So that's why I still see the HING, and then this right here is the terminate null from something. So this also shows why I put the A and the Z in there, because otherwise I wouldn't know what was there. So that's what happened there. Let's look at the string cat function. So I'm going to do this again. I'm going to copy A back to C. Then I'm going to call string cat with B. And we don't need this anymore. And let's see what that looks like. There was string copy, string cat, right here. Appends the string pointed to by source to the end of the string pointed by destination. So it takes the source and copies it to the end of the destination. So basically it picks up where the terminate null is at. So now it's something else. So why didn't it write something space else the way I'm used to seeing it? Because I didn't tell it to put a space in there. If you want a space, you have to put in a space. So I could have done this. This is technically a string literal, but that is a null terminated array of characters. So it consists of two characters, the space character followed by the terminate null. Something else. So if you want a space, you have to tell it to put in a space. So there's three of the commonly used functions. Let's talk about comparing strings. So I'm going to get rid of some of this. So that's cat and car. Let's look at the string compare function. And let's put this in. So B and C are identical. They're both car. So compare A to B, B to A, and C to B. So like the previous functions we saw, this expects to receive two null terminated array of characters. But unlike previous functions, what it returns is something I actually want. So string compare is right here. It returns an int. So it gave me 2 minus 2 and 0. So what's happening? So when I use string compare, and when I had A and B, A was cat, and B was car, what it's doing is taking those array of characters, there's a C, an A, and you really could put these in single quotes if you want to be clear, a T, terminate null, C, A, R, terminate null. And what it's doing is going through character by character, trying to find out how they compare. As long as they're the same, it keeps moving on. But once it finds the mismatch, like here, then it needs to report the order of the mismatch. So the standard, the C standard, C89 standard in particular, says that if the two things are equal, return 0. That's the reason why when I compared B and C, since they were both car, I got 0. If the left character, like in this case the T, comes before the right character, So if left character is, we'll say, comes before, means it would have a lower value, is less than the right value, because it's comparing ASCII values, car, return negative, that is some negative number, and if left character is greater than right character, return positive. So when we had cat and car, we can see I get positive 2. And when we had car and cat, we got negative 2, because now we have the differences, the lowercase r and the lowercase t. All right? And then once again, when I compare car and car, I got 0. So return 0, return negative, return positive. Now 0 obviously is unambiguous, 0 is 0. But what does negative and positive mean? The standard doesn't specify what negative number or what positive number. So if you're using the string compare function that's in GNU C, which is what I'm using here on Linux, what it does, it takes the characters, in this case a T, so this was in the left string, and subtracts to it or from it the other character. In fact, if they're if they're the same all the way across, then you'd have something like T minus T is 0. So a T is 2 characters after R in the ASCII table, right? Because the letters of the alphabet go Q, R, S, T. So even though I don't remember what their ASCII values are, they do differ by 2. But ASCII values are going up as we move to the right through the alphabet. So this right here should be positive 2. And if I have this, this is negative 2, because this number is bigger than this number. If you use GNU C, it returns this number. If you're using Visual Studio, it just returns negative 1 and positive 1 as the negative number and the positive number. So one of the things you have to be careful of when you're writing your code is that if you're trying to understand the order of the words in a dictionary sense, which is where you compare individual characters like you would in a dictionary, right? You go through and you say, I want to find these in the dictionary. If I see car, then I know cat has to come later because T comes later than R. If you're comparing them for order, then you really should look for 0, less than 0, or greater than 0. Don't look specifically for 1 and minus 1 because of this issue here. All right. Now, if I had 2 characters next to each other in GNU C, like S and T, then they do differ by plus or minus 1 depending on the order. But I can't count on that working the same way in Visual Studio, so don't do that unless you know that's really what you're trying to achieve. So that's how that works. So this is used a lot if you want to sort strings. You want to compare the characters. All right? So let's look at one last thing. So now we're going to talk about a topic called string tokenization. You do this if you know how to read. This is a string, right? And we still have the string library. When I read this, and this is written in English, so I'm trained to look for spaces as a way to separate the words in general. There could be commas or semicolons and such. But for the most part in English, spaces are what separate the words. So we would say, in that case, that a space is the delimiter. And then what it separates, delimiter means the separator, i.e. the thing that separates. All right. The space is delimiter, and what remains are the tokens. So that's a token, that's a token, that's a token, that's a token. That's if you read English or other languages that work in a similar way. But in programming, we're not limited to that. I can choose the delimiter to be any character. And what remains will be the tokens, regardless. But let's see how it works. The string toke function, where's it at? Down here, expects to receive the address of a string, at least the first time you use it, and then the address of a string consisting of delimiters. And what it returns is the address of a token. But we have to be very careful in how we use this. So I'm going to do this. Char, star, token, star, delimiter equals. And let's use a space to start with. Now while I'm here, let's be careful. You may think, and remember, if I put the star here, over here, it doesn't matter. So I'm creating 2 pointers here to chars. So you might think I could write something like this. Char, star, and then I'd have token is one of the pointers, and delimiter. But the way C works is it attaches this star to this first thing. So delimiter here is actually just char. And this isn't specific to chars. If I'd written int star token delimiter, this would be a pointer to an int, but del would just be a single int. So you have to make sure that you include the star on each one if you include them as part of the same statement. So token is equal string toke, the string I want to process, and then a string of delimiters. All right. So let's see how that works. This. So token contains the address to the T in this. That's my first token. And so what if I call it again? This is wrong, actually. So let's see what happens. I'll just get this again. If I want to move through this, if I keep giving it the address of a string to process here, it just starts at that address. But the problem is that the string toke function modifies this string, which also means this cannot be a string literal since I can't change those. So if I want to pick up where it left off, I need to do this here. Put in null. And I get this is. And so if I do this, this is a string. All right. But let's see what that did to the string. Int I for I is equal to 0, I is less than, let's get the length up here, because since I modified it, I can't use string length down there and get the correct thing. I want to get its length there in characters as I normally count them. I want to print each individual character in that string. Now I'm going to do the same trick I did before. Put some character that I don't expect to actually show up there at the beginning, some other character at the end. So it wraps what should be there so I can see the unprintable characters. or the things that won't show up. So what do we have here? So here's where we start. There's T, H, I, S. A and Z are touching each other. Why is that? Because when I called string toke the first time, the way I was able to print just this is it inserted a terminating null right there. Or that is, technically, it replaced the delimiter with a terminating null. That's why it shows up here. And then when I called it a second time, it did it after is. So it put it there. When I called it the third time, now it put one there. And so forth. That's what it would keep doing. So when it's doing that, it's modifying the original string, which also means that if you want to get the original string later, because if I come down here and say, okay, now this, printf, and print A, in order to try to print this as a string, it just prints this. This right here came from this because this string has been modified. It's too late to print the whole thing. So had I wanted to be able to print the whole thing down here, I really should have used string copy to make a copy of it first. So this is how I use this function. Now, if we think about scalability, what's the problem with this? Well, I had to know to call string toke exactly 4 times to get the 4 tokens. So what would be a better way if I don't know how many tokens there are going to be? Well, what happens if we call string toke an extra time? I'm technically at the end now, but what will I get? Let's see if this will give me what I need. So this may not work. We'll see what happens. Segmentation fault. Why is that? Well, actually, I ran out of string. But what string toke will return to let you know that it's out of strings or string characters, or tokens, technically, excuse me, is it returns a null. So I can look for that. So let's do this. Wow, token not equal to null. I want to print the token. And I'm going to tokenize once out here because it could be it's an empty string. So there may not even be any tokens. But as we did before, when I initially started on the string, I put the address of the string here. But now if I want to pick up where I left off, each additional call to string toke needs to use null there. This is a string. So now it works. And I can come up here and do this. This is a string to practice with. I don't change anything else. In the previous code where it was hard-coded to use string toke exactly 4 times, I'd have to come back and fix it. Doing this means I didn't have to fix anything. I just changed the string and I can make it shorter and it would still work. All right, so this is how I can use it. Now, sometimes I will do specific things if I need to get, say, for example, if I knew I needed exactly the first 3 tokens, well, then I might call string toke 3 times. And I might have 3 different variables for saving the address if that's what I needed. So now let's talk more about the delimiter. In C, this right here is an array of characters, right? A null terminated array. But I can have multiple delimiters. But it doesn't look for things in pairs. So if I'm trying to look for a specific pair like is, putting in is won't give me that. Instead, it sees the I as a delimiter and it sees S as another delimiter. But I can do this. I might say, well, whenever I see a space, I want to separate it as a token. And I might also want the letter I, for example, as a delimiter. So let's see what happens now. TH, there's an I. So this says that's a delimiter. So TH is a token. Now S is its own token because it's followed by a space. I got rid of the I, so there's another S. So I can do stuff like this. If we only had the I's, now spaces are no longer a delimiter. So TH, delimiter, S, right there, space, and you can't see it here, but there's really a space there. We could do our trick from before to test that out. And did I do that? Yeah. We need to recompile. So see, it does catch the space. That's why I put in the Z there. So S space is a token, I is a delimiter, S space A space S T R is the next token, and so forth. So it's not very robust. It can't handle multiple characters together. So if I was trying to look for IS to treat this as a delimiter, this is the delimiter, and there's no others, it wouldn't find those specifically. But some programming languages will allow that. C is just not robust enough for that. It's also easy to break how this works. So for example, if I have two different strings and I want to tokenize each of those separately and go back and forth. So let's say I want to do this. Another string to practice with. So let's say I want to get this, then another, then is, then string, then a, then two, and so forth. I might think to do this. Token equal string toke, a, and my delimiter. And we'll print it off. And I'm going to reuse the token variable name, but that's not the actual problem here, even though we'll see a problem. So this will be B. And I said earlier, if I'm going to pick up where I left off in A, I need to put null there. So I may do this. And I'm going to change this to this. Okay, I got my this. I got my another. But how do I return to A? When I put in null, it picked up where it left off, which was processing B. So it had zebra. So you may say, okay, I know how to fix that. I just tell it A again. Well, it gave me this because remember, it modified this string. So as far as it's concerned, this is THIS terminate null. That's the whole string. It has no way of knowing that these other characters were part of a larger string because the entire thing is a null terminated array of characters. It has no way of knowing what it started with. So this doesn't work. So if you want to do something like this in C, you have to be a lot more clever, which probably means you make a copy of something and then process the copy and then keep track of where you left off. So I really wouldn't reuse the token variable name then. I would save it like token 1, token 2, and then I could go back and maybe pick up where I left off or something. But I'd have to, it would take a lot more logic to do that, but this clearly doesn't do it. So these are the string library functions I've used most. If you check out the string library, you can see it really has a lot of other functions, including functions for like converting case or doing whatever. It does a lot of other things, but those are the ones I've relied upon the most in what I do. So you may be thinking now, why do I even need things like string tokenization? That doesn't seem that important. Well, the next video topic that I'll work on will be reading and writing files. And for the way we're going to read files, they'll come in as strings. So even if a line of a file has this, you may say, well, that's just 3 numbers. in some sense it's true, but I'm going to save these as a plain text file. So they really will be characters. So it's really the 1, 2, 3 character followed by the comma character followed by a space character and so forth. So I will need to tokenize a line from a file to get the tokens and then convert the string 1, 2, 3. So the way it's going to come in, depending on what I'm doing, will be something like this. And then I'll need to turn that into the integer 123. But I need to know how to tokenize to do that. So that's the reason why we're learning to tokenize now. But it has a lot of use for processing plain text files. But we'll see that in another video.